comments you wanted to make in relation to that? If you have any particular individual comments, please email me, speak with me after class or during office hours, and or email me and I can meet with you another time, through Zoom if you want. Okay, is that? All right, so today we are starting with waves. And what I wanted, in fact, let me see, I may just try to write next to it. And to be able to do that, to write, let me just pull a new one and say notes. Oops. What am I doing here? Okay. And then as I do this, no, that's not, as I do this, in my notes to the left. Okay. I will do it like that, and since you all have it nearby, I think you're going to be able to see all of the details, because then I like to write notes as I'm talking about things. So number one question that everybody has really, and it's a good question, to tell you the truth. Now that we've learned about statics, all right, electrostatics, about how charges generate a static field, how static fields propagate and everything. Why do we not use static fields for everything? Why do we have to go to frequencies, all right, and then talk about AC fields? Have you asked that question yourselves? Do you know, has anybody told you why high frequencies were important? Because it's one more complexity, all right? Why making life difficult if we don't have to? What do you think? Why do you think that we bother with frequencies? And it's not just, it's all frequencies. It's another kind of words. But why did we have to bother like that? What do you think? That is one, of course, yeah. But did we solve a particular problem? Because, just creating more opportunities for something is one thing, but solving a particular problem is another thing, all right? So there was in about 150 years ago, or say in the beginning of the previous century, there was a long debate of whether energy, like power, would be delivered using DC or AC. Have you heard about this historically? The Edison versus, the AC versus DC war. It became an economic war at the end. I mean, there was a time that there were no other news. It's like the war in Ukraine, practically. Today, that you turn on the news. There was a time that all the newspapers write about that. So why do you think AC, even a low frequency, right? Why do you think AC, the power we get it's survived the conflict between, yes.
Travel further distances.
Yes, yes. And why can it travel further distances? Because you have less losses. So for long distances, you prefer AC, all right? For short distances, DC is better, as a matter of fact, because in short distances, you can deliver more energy through DC, all right? So for example, all of our electronics, with the exception of the transmitter, work on DC. So they take AC, there is a small converter, AC to DC, and then they use DC. Why is that? Because it's more effective when the distances are small. All right, so all of the electronics, we're talking about these teeny bitty things that they are in here. I mean, the biggest thing is the battery. With the exception of the receiver, and transmitter. Everything else works on DC. Why the receiver and transmitter work on AC? Because we need to send messages far away. All right, so the need to send something in a long distance make everything else. We have therefore circuits that have both DC and AC. Do you know how much nicer it would have been to have only DC in the circuit design? The AC combination with DC is a tremendous problem. All right, it has been. However, we do it because DC is better for local transmission of power, and AC is better when we want to communicate. So that's number one. Long distance goes further out than the DC. Second, we can modulate. You cannot modulate DC. You cannot modulate DC, but you can modulate AC very effectively. And you can modulate in multiple ways when you are in frequencies, all right? So when you are in a frequency, that's the opportunities come into place. When you are away from DC, then it's not only the frequency you have, it's the band, the frequency band, how many frequencies you can use, how you can modulate them. You can modulate them in amplitude, you can modulate them in phase. There is no phase in DC. And we'll talk about what phase is in AC, all right? So that is the reason we're using AC, and it's very important, obviously. But for circuit designers, DC and AC are equally important. And as a matter of fact, we call it digital and analog, all right? And mixed circuit designs, when you hear mixed, it means analog and digital on the same chip. And also now there is going back to nature, all right? We've learned that yes, DC is very effective in doing things. However, when you start doing a lot of computations, heavy computations on chip, it's not as effective as how nature does it, which is only analog. So people now trying to learn how nature does all of these tremendous computations and then all of the processing of the information, all right, that we get, and try to do also computations in the analog. So we do a lot now of, this is at the research level, all right, where we try to do a lot in the analog domain without necessarily having to go to DC, only for information processing. But for heavy computations, we'll always be DC. Okay, until who knows what's going to happen in many years later. All right, so AC. What is AC? AC is to have a source that produces an alternating signal. All right, so for example, these signals are very easy to express mathematically. This particular case is a cosine signal. And what happens here in this, this is how we show a signal in the physical domain. Along the X, for example, that can be a wave, all right? Usually the way we introduce AC or waves, that's why you call it waves, because the first time we observed them was in water, right? In the sea, you see the waves coming. In a pond, you throw a little rock, and then you see, for example, how the waves form like a cylindrical, they're not cylindrical, but they're like circular waves, and they expand and they go down. It's very interesting to see that, how the waves, when they come into the shore, they're like planes, all right, or like lines, and they come to the shore, but with the same intensity meaning the maximum of the ocean waves when they hit the shore. As a matter of fact, it comes higher. You know why? Because the ground is coming up from the sea. If, for example, I am on the beach and I see the waves coming, and now right here. So this is the water, all right? I mean, this is the bottom of the sea. And then this is, let's assume the water if it's calm. And waves are created from the wind. So it's like the wind pushes the mass, and you know, because of pressures, creates wave, and a wave comes like this here. All right, but then when, let me do a bigger wave. A wave comes like this, for example. It's out of, and then when it comes here, all of the mass is pushed up, all right? And then when you continue like this, so here, for example, a lot of times it hits the shore, and then you see that also the crust goes like this. So waves in the sea, they are coming most probably, if you don't hit the bottom like this, or the bottom is far enough, you see them coming like without any, almost the same kind of the same more or less level. Of course, you know, we say approximately. And then eventually they increase, you know, as they hit, because the mass is pushed up by the bottom of the solid. Now, if you're in a pond, and in a pond, let me do the pond this way. This is the let me see. This is here, say the water. All right, and then what I do is that I throw a rock, and then what it creates here, it creates waves that go like that, but they go lower. Without having, you know, the reason for this attenuation is because when I look from the top, the wave starts here. Let's assume that this shows the peak of the wave. And then the wave goes out like, you remember how we were saying that the electric field will go out if you are in statics? And if I have a charge, the electric field that goes away from the charge as 1 over r squared. And if you have a cylinder, it goes as 1 over r. This goes, as if it were a cylinder, as 1 over r. So the energy from here, the peaks are going down because it distributes along all of these surfaces. So as we go out from one point, for example, if I am observing here, this one up there, so this peak most probably is this here. But then when I come to this peak, so it's approximate, all right? When I come to this peak, this value here is already below that value by 1 over rho, almost ratio. This here is below that by 1 over this distance. This here is below that by 1 over this distance, all right? So practically, as we go down, this dissipates because it spreads out. This one, it comes like lines, you know, like lines, they come like planes, they don't spread, and that's why they remain at the same level. But, and sometimes we see something opposite to this, they increase towards the end because of that phenomenon. But in any case, this is what we observe as humans. We call those waves because they wave in circles. And then eventually we call those waves too. And these are waves we don't see, but these are waves, you know, of electric and magnetic fields. And so how do we create those electric and magnetic fields? We create them with antennas. We are not going to cover this chapter. It's something if we had time we would cover after transmission lines. However, so this concept here, people thought and said, well, okay, if I can create with an antenna a wave like this, then if I, because of this phenomenon, all right, I don't, when I send this wave, let's assume that I want to send this wave from here to the other room down there. So obviously I cannot use DC. That's it, okay. Let's assume I had a huge circuit here. I'm not going to use DC, I'm going to use AC to send this to send my wave with whatever information I have from here there. But then I don't want it to go and spread out, all right? Because if I excite this wave here, if I have an antenna like this, which excites this wave here, and I excite it here, and I let it go, by the time it goes to the other room, it's gonna be, I will be here and the wave is gonna be down there. And therefore the value here, the energy that I will be able to deliver to the instructor in the other room is gonna be smaller than the energy I am sending from here by 1 over rho minimum, if not by 1 over rho squared. If it, excites, if it goes like spheres, all right, it expands as a sphere. So I say, well, that's not a way to send energy from here there, obviously. Now, if I want to send energy from here to another city, to another country, all right, to another state, obviously then I may have to go through this, which is what my phone is doing. All right, my phone is doing that. My phone sends this a wave like this, an electric and magnetic wave like this, that goes like a sphere. But this one connects with the tower, which is who knows where. All right, so I don't have any option without knowing what the tower is. I just let this wave go out, and the tower is sitting there has very small value. But I deal with that. However, if I know where the wave is to go between me and the other instructor, I'm not going to use an antenna to send it. All right. What I will try to think is, how can we confine this wave? We don't want it to go like that. We don't want it to spread out like this. We want to confine it. So we're going to talk about this. This is where the concept of the transmission line comes. All right, when you confine, and you remember how we confine magnetic fields with 2 wires? Remember that? You remember how we confine electric fields by 2 plates? So practically, we're going to, transmission lines are something like that. It's a combination of a wire and a plate. All right, so we'll talk about this. So practically, that's how we confine electric and magnetic fields. But before we go there, let's try to understand a little bit how to represent these fields. So we have sources, which we call oscillators. Why do we call oscillators? A source is an oscillator. Why do we call it like that? Because it creates an excitation. It creates at the end of the source a voltage or a current that changes like that. All right, it oscillates, we call it an oscillator. It's a source. All right, now, how do we express it mathematically? Like this. There are specific things that we are going to define. So, these waves are periodic. All of these functions are periodic. They repeat themselves in this particular case, every length, all right? And the distance between here and the point where you start repeating yourself is called the period of this wave. And we denote it by T. Okay, so this distance in this particular case will define the wavelength also, but I'm going to come to this next. Okay, so now if we were to write this cosine wave, this wave as a cosine in this form in the X domain, then we will also be able to write separately a wave that also changes with time in this way. And then we'll combine the two. So up here, you see a wave that changes only in space. This is this. Waves that change only in space. All right? It's like this. Here are waves that change only in time, which means that I'm sitting here, I don't move, but the wave that I measure, so there is a wave that I have excited, and I'm sitting here as a observer. I don't change my position, but what I measure then changes like this. And therefore, this is a time-varying field, as we call it. And then we express it, this expression here, nothing I have it here. but it's also a cosine. It's a cosine wave that is a function of t, of time t. And I can call this a cosine of omega t. Maybe I have it high. Yes, okay, sorry. Then I write it in this form. It's a very popular form now to write a wave that is excited by a source, all right? So when I say from now on that I have an AC source, I think that my source is gonna excite a wave of this form. My source is gonna be at one point in time, all right? There's no point of having inside this expression for the source that generates the wave, a space coordinate. Because my source generates one wave right here. So this is what the source generates. But the moment the source generates the wave and the wave spreads out, then that wave is both a function of time and space, all right? So if I am the source and generates this, and if you are a observer, one observer, second observer, third observer, and if I send you a wave of this form, then each one of you are gonna measure something different. Why is that? Because the wave is gonna come to you at different times. And therefore, there is gonna be a space coordinate involved, all right, in that wave. So to be able to accommodate that and develop expressions for waves that have both the time and space coordinate in there, so we can make the time constant, or we can make the space constant, or we can allow both of them to vary. This is the most general expression, and that is called the time-space domain, all right? When we show how the wave looks like after the wave has left the source. And after the wave has left the source, depending on where I am as an observer, if I am at this point or at this point, wherever, I'm gonna see then a different value for the wave. And that value is gonna depend both on the time and on space. Okay, because the waves propagate with the same kind of velocity, all right? And it's called the wave velocity. We normally find the velocity from here, you can see next. Now, before we go anywhere else, I want now to define two things. You remember I talked to you about the period. The period is the distance between these 2 points. It's in the time domain, it's called the period. And the period in terms of omega, which is the radial frequency, omega is 2 pi f. All right, so we will use, so these are definitions all now. Whenever you see omega, it's 2 pi f the frequency. And the frequency is measured in hertz, kilohertz, megahertz, gigahertz. All right, a gigahertz, this one operates, not this one in here, I don't exactly know, but my cell phone operates at about 5 gigahertz. It's a very common for 5G or 4G, all right? 10 to the 9. G means 10 to the 9. All right. Omega is the radial frequency of that. You will either see cosine omega t or cosine 2 pi ft, all right? Either one. 2 pi divided by omega, or 1 over f, is the period of the wave, and it's the time period in this particular case. When you express your wave in the time coordinate, it's called the time period. When you express your wave in space, it's called the space period or the wavelength. All right, so you remember, wavelength is defined as this distance between the 2 points when you replicate yourself. And either you are going to call it the space period or the wavelength is the most common. And in time, you're going to call it the time period of the wave. All right, the same 2 points when you start repeating yourself. Now, the time period is related to frequency, and is 1 over f. The wavelength, which is the space period, is gonna be developed. We will see the relationship coming next. But in then a way that varies both in time and space, then I think you will find that if you plot this as a function of x, again, you will define, the period, the wavelength on the basis of that. Now, here explain the wavelengths in units of length, obviously. All right, wavelength in units of length, period in units of time, frequency in units of 1/second, or 1/units of time. All right. Now, there is another thing that we would like. Let me move this out. All right, so we are going to define now another very important parameter, which we're going to call it also the velocity of the wave, or the phase velocity. Okay, and now is where we talk about the concept of phase. The moment, you remember what I said? We started with two waves. One, we express one wave in the space domain, we express another wave in the time domain, and then we combine the two. When we combine the two, then we have this expression here. In terms of time, when we focus on time, and we will always focus on time, you will see that. If I consider that I have this cosine function, which is a function of time at this moment, this coefficient here is going to be called the phase. Why is that? It is not shown necessarily here, but if I were to write the same way as a function of time, so here I have it as a function of space. If I were to write this as a function of time, and then do it like this, then I would probably have it. Let me see, I can do it like this. I'm not excellent here. So at this moment, it's as you can see, it does not start as this one at the peak, but it starts at some other point here. And it starts, what forces it to start at this different point is this number here, the n by x over L. And that's where it brings the concept of space, all right? So when you are at the moment you observe your wave, introduces this here, which we call the phase. And why we call it the phase? Because it changes the position, all right, of the wave in relation to you at a particular time. So when I say that you have two phases in remember, of three phases in your AC, what does it mean? That you have three similar waves that they are sent through the three wires, which are three-phase one, but each one of them has a different part here, which is called the phase. And a lot of times when we focus on the time, we write this wave as a cosine of omega t minus phi. And we call that the phase of the wave, all right? And then so, which in reality, the phase of the wave, it is related to this particular case to distance, but we call it the phase of the wave. We call it the phase because it does lag or lead the wave from what it would be otherwise if it had a phase equal 0, all right? Here. That's how we introduce the concept of phase. Phase. All right, now, from there, we will introduce the concept of traveling velocity. So what does that mean? If I am the source and you are an observer, and I'm sending this wave here, I'm sending this wave here. The wave have created it has a phase. So I'm sending it there. Then let's assume that I mark somehow, okay, that I could mark the wave. I could probably create a small glitch the moment I created the wave. All right, so let's assume that I am the source and I created, I'm here, and I've created the following wave with a small glitch here, somehow, because it turned off my, and the wave I created, this is all fictitious, all right, just so you can understand what I'm trying to. Let's assume that how I created the wave was like this, a small glitch and then it starts now. And then you're measuring. It's gonna take some time before you see that glitch. Now, obviously, in free space, waves propagate very fast, and we will see how they propagate. But the fact that it takes some time for this glitch, for the first time you observe the wave I created, after I created it, so I created a time t equals 0, and it took some time t until you observe it. It means the wave is taking time to travel, right? And how do we find the velocity of this wave? Find the velocity instead of creating a glitch like I did. You go back to what you had there. And we say, okay, I'm going to then do something different. I'm gonna denote this as I have here. I'm gonna denote this one as my point x1 or my time t1, and then I'm gonna denote this as my point x2 or time t2. So for example, you can either do it from the time or space. All right, t1 or t2. So these points are called equal phase points. Why are they called equal phase? Because the phase in which these two is the same. And how much is the phase in these two? 0 or 2 pi. Okay? If you use this expression for this way, or even that expression, all right? To be here, this pi, the phase has to be 0, 2 pi, 4 pi, 6 pi, and 2 pi. All right, so, and if this is 0, this is gonna be 2 pi. This is gonna be 4 pi. All right, this is gonna be 6 pi. So, because we are on a circle with a phase, 0 and 2 pi are the same. So we call these equal phase points. All right, every time you find a point that is repeating itself, that means that they have the phase, the same phase in the previous one, that it was identical. All right. So we are looking at an equal phase point. At this point, x p equals 1, I call it p. And then I'm gonna find out how fast this point moves. And to be able to do that, I take this, which is the argument for this cosine, and I try to make that equal to 0, all right? Because that's exactly what happens here. To find how far away these points are, or in other words, if that were to be in the time domain, how long it took for a point to go from one position to another. Then I have to, first of all, I call these points an equal phase, and then I put that equal to 0, all right? And then from here, I find out how t and x are related. So practically, I will take the derivative. So I will have to find the velocity, and the velocity, the way we find it, as you know, is from dx dt. That's the velocity, all right? This is the definition of velocity. So if this equation expresses, if this one equal to 0, expresses all of these points, all right, here, which means if this point was here at time t equals t1, this point will go here at time t equals t2. All right, that's what happened. So we'll to find out how long it took for this point to go from here to there, we take this expression, all right, this, because this is the characteristic of these points, that they are 0, all of them. And then we take the derivative of that, of dt dx, and then from there we find what we call the phase velocity. And we call it the phase velocity because we find this expression from the phase. All right, phase is this one. The phase of the wave, in reality, is all of this. We call it, not only, in reality, this is the phase, but we take it out of this expression. We call it the phase velocity. All right. And then from this phase velocity, we either find it in this form, or we find it in this form, which is the most important. And then beta is called the phase constant or wave number. So now we have defined the wavelength. Wavelength is in the space domain, the distance between two peaks, for example, or two dips, two peaks. That's the wavelength. Period is 1 over f, is the distance between two peaks in the time domain. Then phase velocity is how fast those peaks propagate in the space domain. And beta is 2 pi over lambda, where lambda is the wavelength, and it's called the phase constant or wave number. And if you define beta, then the phase velocity is omega over beta. These are all definitions. There's nothing to prove about it. It's just we have to define it. And these are all important because we are going to start next time talking about how those waves propagate and how to create them. Okay? All right. Thank you.
Sir,
Yes.
team exam. Okay, this is that
Just a
guy who